Hello everyone, welcome to a new episode of Golang Cafe, and today we're going to go through Advent of Code Day 3. We're going to attempt to solve Day 3 of Advent of Code by using Go. As we've seen in previous episodes, today similarly we have a text input, and our text input is just a representation of a map, and the map is a representation of a field, supposedly, where you have squares and trees represented by a dot and a number sign, as you can see here. This one is a pattern, obviously, so it's not representative of the whole map, and the whole map is using the pattern, using the initial input as a pattern, and it repeats itself from left to right. So as you can see here, you have 11 columns that repeat on the same pattern over and over again. You see all the same pattern all over again, and for the second row the pattern is slightly different, but it still repeats itself on the right hand side indefinitely. So this generates an indefinitely long map, which is indefinitely long on the right, but still has a limit on the height. So the height is limited to the length of the pattern, but on the length is indefinite because it goes ahead and uses the pattern. So our objective is counting the number of trees, but the number of trees, we count the number of trees by traversing the map in a very specific way, as it says in the problem. The way we traverse the map is by going down using a diagonal slope, and we use this diagonal slope specifically by going down 1 unit and going right 3 units. So once we go down 1 unit and right 3 units, that's our first step. The second step is going to be down 1 unit and right 3 units. That's the second step. Third step is down 1 unit and right 3 units, and that's the first step, so and so on and so forth. This is the way that we traverse the map. And where does it end? It ends when we arrive at the bottom of the map. The objective is to count how many trees we would encounter while doing this operation, basically. So the first thing you would think on how you represent this at least this data structure in memory, and how you would then traverse the map. The first thing you would think of is probably to represent most of the map in memory and traverse all of that matrix. So you represent it as a matrix, and then you go through the matrix until you reach the end of the matrix. But that would be very memory intensive because you would have to generate a very large matrix here. So the interesting part here is that we have a pattern, and the pattern, since the pattern repeats itself, we could use the modulo operator. The modulo operator allows us to know a location for this pattern. Doesn't matter the length of the row, it's still relative to the length of the pattern. With the modulo operator, we still know relative to the length of the pattern where we are at. So if we have this one is 11 columns, so if we have column number 13, since this repeats itself, using the modulo operator, we know that 13 modulo 11 is 2, because it's the remainder of the division between 13 and 11. Then 2 is going to be the value of that column relative to the length of the pattern. So, and indeed, if you look at that, you will look at 11, 12, 13, and then you will be at the second, obviously at the second position, which is always the same here because it repeats itself. So let's just get the puzzle input here, and the puzzle input is a pattern much longer than the example that we're seeing here, which is much smaller, but nevertheless we can just copy our input in our file, and then what we're gonna do, we're just going to create our file, our Go file, which we're gonna use to load the data in memory. By, as always, I'm using a util.read the file. You can use any other utility like OpenFile, but I'm using this one because it's quite straightforward, and we also need to check for the error, fatal. So now we just need to split, we need to create the data structure, the main data structure that holds all the data in memory. We said we don't want to store everything here. We just want to store the pattern itself, and then use the modulo operator to see at which position relative to the length of the pattern we are at. So this is just a matrix of characters, and in Go, the way you represent characters is by using the rune code point, which is Unicode code point. So we just use matrix, a slice of slices of runes with length 0, and then we attempt to read the lines. We just use the bytes.splice as we have always done, because we're working with bytes now. So we split the bytes by new line. So here we have each line. If the length of the line is 0, it means that we can just skip this line, and this is going to be the row. So we have the row, and then now once we have the first line in memory, we need to load each character into our matrix. So we just need to iterate over this run here. So it's C range, so we need to range over the line, which is a string. We want to convert it to string first, because otherwise it's going to have just a byte, and then we need to convert that back into run. So we just convert it to string, and then it's automatically converted into run. So when you do a range over the string, is converted automatically, is a run code, Unicode code point. So then here what we can do, we can just basically append row C, and we append our character, and once we created the row, the m is equal to append m row, and that should be our matrix basically. Let's see if we have done it correctly. And here we see that we have loaded all the characters. So these ones are Unicode points as key values of the characters, which is the dot sign and the number sign. But that's fine that they're represented as numbers here. So we said that we have to basically go down all our pattern until we reach the end of the pattern. So we already know which is the length of the pattern, which is just the length of our matrix, like the height of our matrix. So we can go down the height of our matrix. And then we're going to use the modulo operator to see whether we are on a tree or a square. So which is like a number sign or a dot sign. And then we count the number of total trees. So we said we want to count the number of valid trees, and we want to use 2 pointers in this case. So we have a pointer that steps each time of 3 units, and a pointer steps down of 1 unit each time. So we create these 2 pointers, and we increment them accordingly. And we use these two as 2 pointers that we use to access our matrix basically. So is right 3 and down is 1. So until down is less than the length of our matrix, which is the height of our matrix, then we are going to do, we get the row of our matrix, which is the row with the matrix we are on, and then we need to find out in which column we are at on that matrix by using the modulo operator. So row of right modulo the length of the row, which is always the fixed length. We could even figure this out before. So, and if this one is equal to the tree side, the number sign, then this is a tree. So it's just like total. I would rather call this total than valid. Total. And then we increment down by 1 unit each time, and we increment right by 3 units each time. And then we should have the total here, which is 187. And that's what the original answer was. That was quite easy, because we use the modulo operator. It's quite easy for us then, since this is a pattern, it's quite easy to us to know relative to the length of the pattern what the position is on our map and what the value is of our map. Now we have part 2 is fairly similar to the previous one. The input is exactly the same. The logic that we use is exactly the same. What it changes is the frequencies. So we need to count the number of trees, not just by one slope, which is the right tree down 1, but we also have to do for a bunch of other slopes here, which gives us some numbers. So each of those slopes will give us different numbers, and then we need to and then we need to multiply them all together, and that will be the final answer basically. So we already done this one, write 3 down 1, so it's just a matter now to, we could even do copy paste, and we could even then just change the numbers there, because the logic is exactly the same. It's just that we need to repeat this operation. So instead, what we can do, we could just optimize our implementation, and we could create a function that does work down and takes write and down as an integer values. It takes our matrix and return the total count of trees that we encounter using that specific pattern, because you have to think of this write and down as a specific pattern that we use to walk down the matrix. And so the write and the down are effectively our step, the way, you know, the steps that we do each iteration, and then we have our counters. So the down counters is equal to down step, right counters is equal to right step, and then the logic should be exactly the same. So down is less than length of down, length of the matrix. So until the row counter, which is down, is less than the height of the matrix, so we continue iterating and going until the matrix, until the end of the matrix. And then the logic should be pretty much the same here. We just copy this. And the thing that we need to change here now is that we're using different steps, so it's not just 1 and 3. It depends on what the step we have defined. So here is down step, here is right step, and then total as well we need to initialize, it's 0, and total is what we're going to return at the end of this iteration. So now we could easily then, so write 3 down 1, write 3 down 1, write 3 down 1. So what we're gonna do now, we are going to just use this function work down. The right step is 3, the down step is 1. This is our matrix, and this is our result, which we call it dot1. And we are going to use dot1, and we are going to see whether that's the same one as we've expected before. So it's the same one. So what we need to do now, we need to apply the same logic, but we just need to call the function with different parameters. So it's 1 1 5 1 7 1. So if 1 1, so this okay, 3 1 1 1 5 1 7 1. So this is 5 1 1 1 7 1, and the 1 2, the final one is 1 2. So in this one is 1 2. So now this is 5 4 3 and 2, and then the final answer, it says that it's the multiplication of all of those. So it's 2 3 dot 3 dot 4 dot 5, and it's like 472 328 3400, 472 328 400, and that's the actual result that we were expecting. So the second part was quite easy. We're just an optimization of let you optimize the first implementation of the first part basically. So yeah, that's the day 3 of Advent of Code. I hope you liked it, and see you in the next one.